Hey kids, hope your day is going well. Look at these words just appearing on our screen, right? And excuse my squeaky chair. I don't know, I seem like I can't get into any office that has a non-squeaky chair. All right, so remember that what we've done before is we have learned how to solve differential equations. But remember, that just means getting rid of derivatives. Sometimes your answer is plus c. Sometimes I give you an initial value so you can solve for the c. Sometimes you have to recognize the differential equations when you're doing acceleration as to go back to velocity and position. Sometimes you have to recognize that it is a separable differential equation. And you have to do algebra first and separate and get the y dy stuff and the x dx stuff on opposite sides of an equation. Then we learned how to approximate a solution. So instead of solving a differential equation, you approximated the solution of a differential equation with Euler's method, which used an initial value as your fact point, and then Euler's method got you a number of fiction points. Use fact and the derivative to get a bunch of fiction points, right? And then you could plot those points if you wanted. If you plotted the fact and your fiction, then you could get an approximate shape of the original, an approximate shape, right? So what we are going to do now is learn another approximation method. And this method is a method of getting a picture. Just like Euler's method got you points, you had to plot the points to get an approximate graph of the solution. Now I'm going to teach you not Euler's method, but you still are going to get a picture of the solution, and that picture has a special name, and it is called a slope field. They are mostly done on computers, and all you have to do, again, this is super easy to Google, Desmos, GeoGebra, just ask for slope fields and you'll see. They're very easy. What you're going to be tested on, very easy to pull up, right, and get. But what AP is going to ask you to do is one of two things. They're either going to ask you to draw a very simple one yourself by hand, or two, they're going to ask you to interpret a given one. Okay, so those are the two things that we're going to teach you how to do. Draw a simple one by hand, and what to talk about if they ask you to interpret a slope field. Direction fields is a synonym for slope fields. Direction fields, that language is used more, I think, in physics and in multivariable than in AP. AP always calls them slope fields. Whoa, you see what happened there? So the nice thing about slope fields, it is drawing. You're going to draw cute little linearizations. And remember, linearizations are just tangent lines. And you've been drawing and approximating what a tangent line looks like for a long time. They're so cute. Slope fields are so cute. So here we go. Here is a differential equation. This is a differential equation. dy dx is equal to 2x. You know how to integrate that, right? You can actually get the real solution. We're going to pretend that you don't know. So make yourself a little chart, and I'm going to pick some points for you, and AP will do this as well. They'll tell you what points they want you to draw. So when X is 0 and Y is 0, I want you to figure out the slope. So X is 0 and Y is 0. In this differential equation, the slope only depends upon X. So 2 times 0 is 0. And what I want you to do on this grid is at the point 0, 0, I'm going to draw a point, but that's not the slope field. The point at 0, 0, and what I want you to do at 0, 0 is draw me a tangent line with this slope. So at the point 0, 0, draw a short little linearization. Now I want you to do that, right? Cute. I want you to do that at the point 0, 1. Then guess what I want you to do? I want you to do that at the point 0, 2. Then I want you to do that at the point 0, 3. Can you see the pattern here? So I've just taught you how to create part of a slope field. Now let's talk about what that would mean if I was asked to interpret. Without writing the rest of these down in my table, can you tell an interpretation would be there are horizontal tangents everywhere X is equal to 0, right? That's an interpretation of what we just did. No matter what the Y value, notice the derivative doesn't depend on Y. So regardless of the Y value, everywhere X is 0, you're going to have a horizontal tangent. And remember, we kind of care about what horizontal tangents are. I forgot that I typed that in. Okay, there's the interpretation, pattern recognition. Now I'm going to move to the point 1, 0. Go to your slope, plug in the X and the Y. Psych, you don't have to plug in the Y value because your derivative doesn't depend on Y. And I got 2. 2 times 1 is 2. Can you draw a little cute little tangent line that has a slope of approximately 2? Bam, done. Can you see that that's going to happen everywhere X is 1? I don't really have to keep going with my table, right? So notice that here, everywhere X is 0, I had a pattern. Everywhere X is 1, I see a pattern. Not only is it 2, it's positive. And remember, we care about when derivatives are positive, right? Now I'm going to move further along the x-axis to 2. I don't really think I need all that many, right, points. I think I can figure this out. I'm going to draw a slope segment of 4 at the point 2, 0. And I'm pretty sure vertically, because my derivative only depends upon X, the slopes are going to be the same everywhere X is the same. That's my pattern. That time I only needed 1 point, right? I kind of got the pattern and I can talk about the pattern. I think I'll go investigate what's happening for the negatives. At the point, -1 comma 0, what's my slope? -2. Once again, feel pretty confident about my ability to generalize with a pattern. How about at -2, 0? Slope of -4, copy and paste. So here are some things that I might say about my slope field. If I'm asked to interpret, not only am I going to chunk here, but I might say all the way here, what's my pattern? My pattern are all the points where x is equal to 0, I have a horizontal tangent. As x moves from 1 to 2 and then to 3 and 4, what's happening to the slopes? Right? As you move from 1 to 2, and it doesn't matter the level, your slopes are positive and getting steeper as x increases, right? 1, 2, at 3, the slope would be 6. At 10, the slopes would all be 20. And then what about when x is negative? When x is negative, you have a beautiful symmetry, right? When x is -1, when x is -2, slopes are all negative and getting more negative. And further, I see symmetry. Right? Do you see the symmetry? That at 1 comma 0, the slope is 2, and at -1 comma 0, the slopes are -2. Right? All to the right of the y-axis, I have positive slopes. To the left of the y-axis, I have negative slopes. And on the y-axis, I have slopes that are equal to 0. So in other words, your slopes change from negative to 0 to positive. Do you see what I see? In your slope field, do you see x squared plus a vertical shift? There it is, right? It's kind of like those magic eye puzzle books, right? When you kind of like blur your eyes and like something comes out 3D at you. Well, if you are looking at this slope field, you can see the solution. So this is the slope field that goes, you made a slope field for y prime is equal to 2x. And what you see is the solution to y prime is equal to 2x. Now, you know what the solution to this is. You know that. But if you couldn't integrate, you can kind of sort of see the solutions. Here's what also AP will ask you. If they give you the initial condition like 1, -2, plot that point and make it obvious. And then they're going to want you to sketch the particular solution. Now, I see x squared plus c, but they're going to ask you to sketch through an unknown. So what they want you to do is start with the initial condition and then let the slope fields guide you. So as x is moving right, your slopes are getting steeper and steeper. So your graph should get steeper and steeper. Glide along. Don't ever cross a slope field, right? Perpendicular, right? The slope fields are your guidance, right? Then as you go left, your slope should approach 0. And then your slopes change sign, so you should have a turning point. You see the symmetry in your slope field, so directly the same distance from the y-axis as 1, -2 is, you should be over here, and let your slopes are getting more and more steep, so your graph should get steeper and steeper. That's me sketching the particular solution through the initial condition. Given the derivative, and I generated a slope field. So given the derivative, sketch a slope field, sketch the initial condition, or sketch the solution with the given 1, -2. This time they didn't ask you to interpret. Oh, look, my sketch was worse than the computer sketch. Now, it is true, AP will be pretty flexible with this, right? You don't have to be exact. It is a sketch. My yellow graph would get full credit, even though it doesn't absolutely match the red one. By following what the direction of the tangent lines and the slope or the magnitude of the tangent lines tell you, you can follow those directions and get a picture of the curve. So what if I gave you a different one? What if I said through 0, 1? Plot the point, label it. Whoops. Sketch. Right? There you go. Check. So let's practice. Given a differential equation, right? Y prime is equal to cosine x. Think about what the slopes, the derivative only depends upon x, doesn't depend upon y, and the cosine of 0 is 1. So look at all those slopes that I drew. At x equals 0, y prime so I drew a bunch of slopes of 1. Then I did plus and minus pi. Cosine of negative pi, right? Negative pi, and cosine of pi, positive pi. -1. There's all my slopes. Again, notice the vertical pattern because my derivative only depended upon the x value. So what do you think would happen if your derivative only depended on y value? What do you think? That's called foreshadowing. Notice now I picked pi over 2. So what is the derivative at positive and negative pi over 2? Cosine of negative pi over 2 or cosine of pi over 2? 0. Right? So I had the horizontal tangents there at the pi over 2's. And then lastly, I did 2 pi. What is the antiderivative of cosine? You know that. You don't need a slope field to tell you that the antiderivative of cosine is sine x plus c. Do you see sine x plus c here? See it? If I start, for instance, at 0, 0, right? Slopes positive, going, increasing, but going to 0. Then my slopes are negative. Slope is -1. I got to get back down. I got to get to a slope of 0, right? Crazy. That's what a slope field is. Drawing a bunch of little slopes given the derivative and then looking at the picture to try to see the solution. Woohoo! Look at this one though. Given the differential equation, you do not know what y equals. You do not have the technique to solve and get y by itself, to get rid of the derivative. You don't know what y is equal to. So can you get a picture of the solution? So AP tends to give you problems like this where it's the black dots are where they expect you to draw a tangent line. So you make yourself a little table and you just say at every one of these points, they're going to want you to draw a tangent line. Whoops, sorry. So you're going to pick the point 1, -1, 1, 0, 1, 2, whoops, sorry, 1, 1, and 1, 2. And then you're going to go put that point into the derivative. Now remember, the derivative this time doesn't depend on, right? It doesn't depend on just x. This time, 2 plus 1 is 3. So through this point, I'm going to draw a little tangent line that has a slope of approximately 3. But into the derivative here, into each one of those, ooh, you like to know where horizontal tangents are, right? So at the point 1, 0, I'm drawing a slope of 2, so less steep than the one I just drew. At the point 1, 1, a slope of 1, and a point at the point 1, 2, a slope of 0. So this is slightly annoying to do by hand, right? But that's literally all there is to it. Literally all there is to drawing it yourself. So that's objective 1. Draw your own slope field. They won't give you the one that I did before, like y prime is equal to 2x. No, they're going to give you one like this. This is D from the homework, right? So I just started one of your homework on the handout. The other thing that they'll ask you, as I said, was interpret. One of the ways they can ask you to interpret is to match, to ask you to match. So this is also on the handout. When they want to ask you to match the slope fields with their differential equations. So they want to know which one of these slope fields was generated from 1/2 x plus 1. This shouldn't be too hard to figure out because you know how to anti-differentiate that. What is y? Right? Power up, divide by the power up. Which one of those graphs looks like 1/4 x squared plus x plus some constant? Right? Do you see a parabolic shape in any of those? Maybe this one? Right? You see kind of a wide parabola in there? Let me skip. So this one was being able to recognize, look at this. Look at this one over here. Y prime, the derivative, the slope is the same as the y value. What do you think that would be? So y prime is equal to y. So take a moment and think for yourself. Okay, well, what if y was 0? When y is 0, what is your derivative? Where is y equal to 0? Hey, when y is equal to a positive number, which is in quadrant 1, what's the value of all your slopes? Positive or negative? And getting steeper and steeper, right? Getting steeper as y gets steeper. Where else would you have positive slopes if your derivative is only in terms of y? Quadrant 2, right? Isn't that what happens over here? Positive slopes. And where would you have negative slopes? If your derivative is equal to the y coordinate of any point, you better have negative slopes here. Right? So you see how I interpreted the slope field and its differential equation? I said to myself, what would happen if my slopes was 0? What about when my slopes were 1? Slopes were 2, right? At the point when y is equal to 1, 2, or 0, right? So now let's look at these two. These two are a little bit challenging, right? They're definitely not things that I have seen before. So the slope is x minus y. So in other words, the difference of the x coordinate. So where is your slope going to be equal to 0? Where are you going to have horizontal tangents? Aren't you going to have a horizontal tangent everywhere x is equal to y? Right? At the point 1, 1, at the point 2, 2, at the point 3, 3, aren't you going to have a horizontal tangent? Do you see that in either one of the graphs we have left? Do you see that situation? Right? 1, 1, 2, 2, 3, 3, 4, 4. I'm kind of doing a bad job at that, but I think you get it. Right? And then you can pick other points and see if your first guess works. So I don't know. Let's see at the point, I don't know, -5, 6. Right? -5, 6. So what if this was -5 and 6? What would the slope be? -5 minus 6 is -11. At about -5, -6. Do I see a negative and almost vertical slope? Yeah. It's kind of hard to tell there, but right. So that's how I guess and check. This one goes all the way back to the summer packet. Check this out. Well, no, I shouldn't say that. Let me just go back to think about what this means. Your derivative is equal to the opposite of the ratio of x and y. So what does that mean? Well, firstly, you have a derivative. I'm sorry, you have something in your denominator. Y is in your denominator. So y prime does not exist when y is equal to 0. So you should have no slope drawn there. No slope lines wherever y is equal to 0. Now that's hard to tell on this graph, but there's no extra slope lines drawn. It's because it's horizontal. But also, when do you have a slope of 0? When x is equal to 0, right? How do you make a fraction equal to 0 when x is equal to 0? So every time x is equal to 0, except for when y is equal to 0 as well, you should have a horizontal tangent. You see that here? What else when you have a ratio that's equal to 1? Everywhere x is equal to y, you should have slope lines of -1. So at 1, 1, -1. At 2, 2, a slope of -1. At 3, right? So that's how I interpret. I should have a slope of +1 wherever x and y are exactly opposite, like 3 and -3. So 3, -3, Yep, slope of 1. That's how you interpret slope fields. This time they didn't ask me to write anything, but if they did ask me to write, that's the kind of things I would talk about, where my slopes should be horizontal, where the slopes should be positive, where they should be negative. Aren't they so very cute? All right, so that's your first introduction to slope fields. We'll do some more when we get together. And there's some really good websites to practice looking at slope fields and interpreting slope fields that we'll share with you in our next live session.